Welcome to the deep dive. Today, we're launching into a truly thrilling concept that feels like it's ripped straight from science fiction, but it's hurtling towards reality. Commercial hypersonic flight.
It really does sound like sci-fi, doesn't it?
Totally. Imagine breakfast in New York and dinner in Tokyo after a flight of less than 2 hours. Or crossing the Atlantic, London to New York in maybe just 45 minutes. That's the audacious promise we're unpacking.
Yeah, the speed possibilities are, well, staggering.
For this deep dive, we pulled together a fascinating stack of sources, everything from comprehensive guides by technologists like Taylor Emerell to breaking aviation news reports, and even some really visionary design concepts like Oscar Vignal's AMN.
Right. So our mission today is really to demystify hypersonic flight. What defines it? What are the immense technological hurdles it faces?
Exactly. And who are the key players pushing it forward?
And, critically, its real-world environmental and economic implications. We'll be distilling insights from government bodies, leading aerospace engineering experts, and commercial innovators.
Giving you, our listener, a crystal clear understanding of this next frontier in aviation.
Hopefully, yeah.
Okay, so let's kick things off by defining our terms. What exactly is hypersonic speed? And why is it such a, monumental leap beyond even supersonic travel, which we briefly saw with the Concorde?
Right. So hypersonic speed is generally defined as exceeding Mach 5.
Mach 5, 5 times the speed of sound.
Exactly, which is roughly, 3,836 miles per hour at sea level, give or take? The allure, as you mentioned, is drastically reduced air travel times.
Yeah.
We're talking about journeys like New York to Tokyo in under 3 hours, or even London to Los Angeles in just 90 minutes, as envisioned for a concept like the AHIM.
And London to New York, maybe 45 minutes.
So that's the dream some concepts are chasing, yeah.
That speed is absolutely staggering. But, okay, if supersonic flight was achieved decades ago with Concorde, what exactly makes going beyond Mach 5 so fundamentally different? Why has it remained largely out of reach for commercial aviation until, potentially now? What's the core challenge?
It boils down to a really complex interplay of physics, material science, and radically different propulsion technology.
Okay.
Supersonic aircraft, like Concorde, they used pretty conventional jet engines, just pushed to their absolute limits, with spinning turbines.
Right.
Hypersonic vehicles, however, often require these advanced propulsion systems, like scramjets.
Scramjets. Okay, I've heard that term.
Yeah. They're air-breathing engines that ignite fuel in a stream of supersonic air.
Wait, supersonic air inside the engine?
Exactly. It's a truly mind-bending concept, and they present immense engineering challenges, particularly in managing the intense heat and pressure generated at Mach 5 and above.
That sounds incredibly difficult, like lighting a match in a hurricane, but faster.
That's actually a pretty good analogy, yeah.
So if these scramjets are the key, how exactly do they work? What makes them so critical?
Well, what's truly fascinating about scramjets is how they kind of defy conventional propulsion thinking. They don't just handle supersonic airflow, they harness it. So instead of using delicate rotating turbine blades, which would just melt or disintegrate under that kind of heat and speed, they use the aircraft's own massive forward velocity to ram compress the incoming air.
Ah, so the speed itself does the compression.
Precisely. This allows for sustained supersonic airflow through the entire engine, enabling fuel burning at speeds that would, frankly, tear apart traditional engines.
Wow.
But their design and operation are incredibly complex. You need unbelievably precise control over airflow, fuel injection, and combustion processes, all happening within milliseconds.
Milliseconds.
Yeah. Organizations like DARPA, the Defense Advanced Research Projects Agency, they're actively funding research into these advanced designs. Things like the Hypersonic Air-Breathing Weapon Concept or HAWC program.
Okay, so military funding is a big driver here.
Often is with this kind of cutting-edge tech.
So they turn the very speed that would destroy a normal engine into its power source. That's wild. But with that kind of speed and engine power, you're not just generating thrust.
Right.
You're generating immense heat.
Oh, unbelievable amounts of heat.
How do you stop the plane from literally melting in midair? That sounds like a huge materials challenge.
It absolutely is. That's where thermal protection systems, or TPS, become paramount.
TPS, got it.
At hypersonic speeds, just the air friction alone can generate temperatures exceeding 2,000 degrees Celsius.
2,000 degrees?
Yeah, I mean, that's hot enough to vaporize most metals we commonly use.
So what do you use instead?
Well, we're talking about really revolutionary materials. Things like Ablative materials that literally burn away in a controlled manner to dissipate heat.
Like on spacecraft reentry.
Similar concept, yeah. Or actively cooled panels that use circulating coolants, kind of like a high-tech radiator woven into the skin. And then there are ceramic matrix composites, CMCs.
BMCs.
Yeah, they're incredibly light, but unbelievably resistant to extreme temperatures. And material science is focusing on creating lightweight, durable, and crucially cost-effective solutions.
Cost-effective being the key word there, eventually.
Eventually, yes. They're even exploring exotic alloys with elements like hafnium and rhenium, chosen specifically for their almost unparalleled ability to maintain structural integrity at temperatures that would turn steel into, well, liquid.
So we're inventing entirely new ways to build a plane, not just faster engines. It's the whole package.
It has to be.
And beyond just keeping the plane from melting, how do you even control something moving that fast? Is it like flying a normal plane, just faster?
Not at all. Aerodynamic design and control are equally challenging. Maintaining stability at Mach 5 and beyond requires a really sophisticated understanding of complex airflow patterns and shock waves.
Shockwaves, right.
Engineers rely heavily on advanced tools like computational fluid dynamics or CFD.
So supercomputers simulating the airflow.
Exactly. Powerful computer simulations to predict how air flows around the aircraft, and that's combined with extensive wind tunnel testing, of course.
And what about the elephant in the room, the infamous sonic boom that plagued Concorde? Will these be even worse?
That's a huge question. Yes, the sonic boom generated by hypersonic aircraft poses an even more significant barrier, especially for any potential overland commercial routes.
Which Concorde couldn't really do supersonically?
Precisely. Mitigating the intensity of this boom is a key research area. People are looking at advanced aerodynamic shaping, innovative flight control strategies.
Building on work like NASA's Quest, the quiet supersonic demonstrator.
Exactly. That kind of research is vital if hypersonic flight is ever going to be commercially viable over land.
So what does this all mean for the immediate future? I mean, who are the key players pushing this technology forward from these complex concepts towards actual reality right now?
Well, if we connect this to the bigger picture, you see a truly global effort. It involves governments, commercial companies, and research institutions all sort of working in parallel, sometimes together.
Okay.
The U.S. military, primarily through DARPA, as we mentioned, has been a major driver. Programs like HAWC and the Tactical Boost Glide, or TBG, Tactical Boost Glide. It's fascinating how the extreme demands of these military applications often accelerate breakthroughs.
Yeah, you said
that then have significant civilian applications. It essentially de-risks some of the core technologies, like the scramjets and those advanced thermal protection systems.
It's a unique way for cutting-edge tech to kind of trickle down, I guess.
Yeah.
But beyond the military, are commercial companies seriously working on this? Yeah. Or is it still largely theoretical for passenger travel?
Oh, absolutely they are. You have companies like Hermeus, for instance. They're actively developing Mach 5 passenger aircraft concepts with pretty ambitious plans.
Mach 5 passenger planes.
Yeah. Then there's Reaction Engines in the UK. They've got their Sabre engine, that's synergetic air-breathing rocket engine.
It's Sabre. Okay.
It's a groundbreaking hybrid engine. It's designed to operate both as an air-breathing jet and as a rocket.
A jet and a rocket. How does that work?
It transitions between modes, potentially enabling single-staged orbit capabilities. So it effectively blurs the lines between air travel and space travel.
Wow. That's a whole other level.
It really is. And the UK Space Agency is deeply involved with them, which shows significant government confidence in the project.
And even companies focused on just supersonic, like Boom.
Yeah, even Boom Supersonic, though they're primarily focused on, Mach 1.7, not Mach 5 plus.
Right.
They still contribute valuable data on high-speed aircraft design, operations, and, importantly, sonic boom management. And United Airlines has even placed an order for their Overture aircraft. So that whole sector is moving.
Okay. And we've even heard about some truly ambitious concepts that push the boundaries, like that AHM you mentioned earlier. What makes that one stand out?
Right. Oscar Vignal's AHM Hypersonic Airmaster concept. It's definitely visionary. It's designed to cruise at Mach 7.3.
Mach 7.3. That's over 5,600 miles per hour.
Yeah, potentially cutting that London to New York flight time down to just 45 minutes, theoretically.
Incredible. What else is special about it?
Well, what stands out is its kind of holistic approach. It proposes using hydrogen fuel, which would be much better for the environment.
Hydrogen. Okay. Big infrastructure challenge there, though.
Huge. But potentially zero carbon emissions from the aircraft itself. It also features a highly complex combined cycle engine.
More complexity.
Oh, yeah. Integrating a turbojet for lower speeds, a ramjet for supersonic, and even an oblique detonation engine.
Oblique detonation. What's that?
It's a really cutting-edge propulsion concept where combustion actually occurs within a controlled detonation wave, even more efficient at extreme speeds than a scramjet, potentially.
Okay, my head hurts slightly.
Yeah, it's advanced stuff. Plus, the AHYN concept aims for a sonic boom mitigation system to hopefully allow overland flights, and it even imagines a luxury cabin with, like, virtual panoramic displays for passengers instead of windows.
So windows might be a thing of the past at these speeds.
Possibly, or virtual ones might be safer and lighter. It's really a blueprint for what a sustainable, ultra-fast future could look like.
So it's not just corporations and government agencies driving this. Universities and international groups are heavily involved too.
Oh, definitely. Universities and research institutions worldwide are doing the fundamental research in areas like hypersonic aerodynamics, materials science. They're training the next generation of aerospace engineers who will actually build this stuff.
Right, you need the people.
Exactly. And international collaboration is also essential, involving entities like the European Space Agency, ESA, pooling resources, sharing expertise, and eventually standardizing regulations for such a complex, globally impacting technology. It just makes sense.
Yeah, no one country can probably do it all alone.
Likely not, no.
Okay, all this speed sounds incredible, but I can't help but circle back to the environmental implications.
Yeah.
Are we simply trading shorter travel times for an even bigger carbon footprint? Especially when, the whole aviation industry is trying hard to decarbonize.
That's a critical consideration. And honestly, it's something the aerospace community is grappling with head on right now.
Because these engines must burn a lot of fuel.
Immense amounts. And it's not just the CO2. Unlike current long-haul flights that mostly operate in the troposphere, hypersonic jets would cruise much higher, closer to or even in the stratosphere.
Okay, why does that matter?
Well, it raises unique concerns. Emissions like nitrogen oxides, NOx, at those high altitudes could have a more direct and potent effect on ozone depletion than the emissions from current planes flying lower down.
So it's not just how much they emit, but where they emit it.
Exactly. The challenge isn't just reducing overall emissions, but managing them at an entirely different atmospheric level. The community is actively exploring alternative fuels, like sustainable aviation fuels, SAF.
SAFs, right. We hear a lot about those.
And even hydrogen, as we mentioned with the AHYM concept, to try and reduce that carbon footprint. But there are huge challenges with both producing enough SAF and handling hydrogen.
It sounds like a major hurdle.
Yeah.
What do the experts say?
Well, someone like Dr. Emily Carter, a researcher in sustainable aerospace propulsion at Princeton, basically notes that the transition to sustainable fuels is not merely an option, but a necessity for the long-term viability of hypersonic commercial aviation. It has to happen.
A necessity.
Oh, okay.
And what about the noise? You mentioned mitigating the sonic boom earlier, but how realistic is that? Will these things just unleash these incredibly disruptive booms, making them unusable over land?
You're right to puss on that. The physics are tough. The sonic booms produced at Mach 5 and beyond can indeed be far more disruptive than those from supersonic aircraft.
More disruptive than Concordes?
Potentially, yes. Affecting populated areas even at considerable distances. Careful route planning, mostly over oceans, is one strategy.
The Concorde strategy.
Pretty much. But the real goal is developing technologies to actively mitigate those booms, making them more of a sonic thump. That ability to fly over land without major public disruption is absolutely key to widespread commercial acceptance.
Definitely. Okay, this all sounds like a massive undertaking, not just technically, but also financially and regulatorily. How feasible is this economically, and who's actually going to get to fly on these things if they become a reality?
Is it just for the super rich?
The economic feasibility is,
Yeah.
Well, it's a multifaceted challenge, and frankly, it's a major hurdle right now.
I bet.
Development costs are immense, astronomical, requiring substantial long-term investment from both governments, often leveraging that military R&D we talked about, and private companies willing to take a big risk.
And then operating costs.
Also significantly high. I mean, think about the fuel consumption, the specialized maintenance needed for these exotic materials and incredibly complex engine systems.
Yeah, it doesn't sound cheap to run.
Not at all. So this will almost certainly limit the initial market to a very niche segment. Business travelers on urgent trips, wealthy individuals.
So maybe not for your average holidaymaker, at least not for a long time.
Probably not initially, no. So looking at the big picture then, what does this all mean for the future of travel, for for you, our listener, and maybe for society at large?
That's a really important question about the broader societal impact. There's a quote from Dr. Emily Carter, actually, a different Dr. Emily Carter, an aerospace economist at MIT this time.
Okay, common name in the field.
Apparently. She stated essentially that the societal impact of hypersonic travel will depend directly on its accessibility.
Makes sense.
If it remains a luxury exclusively for the elite, it could inadvertently widen the gap between the haves and have-nots. However, she says, if costs can be significantly reduced and it becomes more broadly available, it truly has the potential to revolutionize global commerce and cultural exchange.
So democratization is key to it having a positive societal impact.
Absolutely. And beyond just the economics, public perception and acceptance are crucial, especially regarding the environmental impact and the noise. That needs a holistic approach, considering not just emissions and noise, but also manufacturing processes, end-of-life disposal, even things like high-altitude contrail formation. It all needs to be factored in for long-term sustainability.
Right. It's a huge system to consider.
It really is.
Well, we've taken quite the deep dive into the fascinating and frankly complex world of commercial hypersonic flight. We've explored the immense technological breakthroughs needed in propulsion and material.
Yeah, the scramjets, the TPS.
The pioneering companies and government initiatives driving this forward, and those really critical environmental and economic questions that still need solid answers before this becomes a widespread reality.
Definitely. From scramjets that literally ignite fuel in supersonic air to materials designed to withstand temperatures hotter than molten lava. And from that ambitious goal of a 45-minute flight from London to New York to the vital need for sustainable fuels and quieter flight paths, it's clear that the sky is the limit is maybe not the right phrase here. We're pushing way beyond that.
Yeah, maybe the edge of space is the limit now.
Something like that. We're witnessing humanity pushing the very boundaries of physics and engineering.
And this isn't just about getting somewhere faster, is it? It feels like it's about fundamentally reimagining our global connections, how we interact with the sheer geography of our planet.
I think so.
What stands out to you, our listener, from this deep dive? Perhaps it's the thought that someday, maybe in your lifetime, a business trip across continents could genuinely feel like a morning commute.
Or perhaps it's that the extreme engineering challenges, we talked about those materials, the cooling systems could spark entirely new scientific breakthroughs that find surprising applications back here on Earth in our everyday lives.
That's a great point. The spin-offs could be huge.
Could be. So, consider this final thought. If humanity does master sustained, efficient, and truly accessible hypersonic flight, and that's a big if, requiring not just speed, but sustainability and, a conscience.
Right.
What other seemingly impossible boundaries might we be able to break through in the years to come? The sheer ingenuity required for this challenge, it really hints at a future with possibilities we can barely even conceive of right now.